Hello everyone, my name is Muhammad Farhan bin Fadili. My number metric is CD250276. Today we are discussing the experimental theory of beam. In structural engineering, beams are members designed to carry loads applied along their length. These loads can be concentrated at specific point or distributed across a surface. And next is design and geometry. When designing a beam, our main priority is a safety. We must select the appropriate material and cross-section so the beam can support these loads without structural failure. So the next is internal force. For the internal force, when external loads are applied, they create internal reaction like specifically shear force and bending moment. For prismatic beams, which are straight member with a uniform shape, our design focus on finding the maximum values of this force. So the next is analysis tools. To the analysis tools, to visualize this, we use a shear force diagram in a short form SFD and bending moment diagram, and in the short form is a BMD. This diagram allows us to see how the shear force and bending moment change at various points along the beam length. Next, the last is stress and equilibrium. For the stress and equilibrium, finally, to calculate the maximum normal stress and shear stress, we must identify the critical internal force. We do this by cutting a section through the beam and applying equilibrium equation to either side. By following standard sign convention, we can accurately determine the force that lead to the final stress calculation. So next, I will pass to my friend. Thank you.
Hai, Assalamualaikum. Nama saya Muhammad Amir Hakim bin Azhar. Nombor metrik saya CD250252 dan saya akan menerangkan tentang observation dalam eksperimen ini. Jadi eksperimen ini berjaya menunjukkan kelakuan shear force dalam simply support beam di bawah dua keadaan bebanan yang berbeza. Okey, daripada eksperimen 1 yang menguji kesan satu beban tumpu yang meningkat. Okey, ini adalah satu trend yang jelas yang telah diperhatikan, iaitu apabila beban yang dikenakan meningkat dari 0.98 Newton kepada 4.91 Newton. Okey, jadi nilai kedua-dua nilai daya shear force eksperimen dan juga nilai shear force teori juga turut meningkat. Ini menunjukkan bahawa hubungan linear secara langsung antara beban tumpu yang dikenakan dengan shear force pada bahagian keratan tersebut adalah wujud. Okey, walau bagaimanapun terdapat perbezaan yang konsisten antara nilai eksperimen dengan nilai teori, di mana bacaan eksperimen sedikit lebih rendah ataupun sedikit lebih tinggi daripada apa yang nilai teori lah. Hal ini disebabkan mungkin akibat daripada geseran pada alat radas ataupun ralat pengukuran yang kecil. Okey, jadi dalam eksperimen 2 yang melibatkan pelbagai konfigurasi beban, shear force didapati sangat bergantung kepada lokasi dengan magnitud beban, iaitu W1 dan W2, seperti yang ditunjukkan oleh nilai tindak balas penyokong RA dan RB serta nilai shear force yang terhasil. Okey, secara keseluruhan, walaupun bacaan eksperimen ini tak sepadan sepenuhnya dengan nilai pengiraan daripada teori, tapi ini menunjukkan bahawa shear force meningkat dengan peningkatan beban dan berubah mengikut kedudukan beban yang telah disahkan. Okey, sekian sahaja daripada saya. Terima kasih.
Okay, for the result, experimental shear force values were generally lower than theoretical values. This difference is attributed to factors like friction within the apparatus and slight measurement errors. The relationship between the load and shear appears to be roughly linear. As you can see at the table 8.2, result from experiment 1. Mass 0, load 0.01, and
experimental shear force 0.01 times 0.26 over 0.44 equals to 0.0059 newtons. Theoretical shear force equals to 0. When the mass is 100, load 0.06 newtons, 0.06 times 0.26 over 0.44 equals to 0.0355 newton. And the theoretical shear force 0.98 times 0.26 over 0.44 equals to 0.580 newton. When the mass is 200, load is 0.01.2 newton, 0.01.2 times 0.26 over 0.44 equals to 0.7091 newton. Theoretical shear force 1.96 times 0.26 over 0.44 equals to 1.160 newton. And when the mass is 300, 01.7 newtons, experimental shear force equals to 0.7 times 0.26 over 0.44 equals to 1.0045 newton. And theoretical shear force 2.94 times 0.26 over 0.44 equals to 1.740 newton. When the mass is 400, load 2.3 newton. Experimental shear force 2.3 times 0.26 over 0.44 equals to 1.3591 newton. For the theoretical shear force 3.92 times 0.26 over 0.44 equals to 2.320 newton. When the mass is 500, load 2.8 newtons. Experimental shear force 2.8 times 0.26 over 0.44 equals to 1.6545 newton. Theoretical shear force 4.90 times 0.26 over 0.44 equals to 2.900 newton. Okay, for the table 8.3 result for experiment 2, figure 8.6, 3.92, and the weight is 0, force 0, experimental shear force is negative 0.09, and RA Newton 0.053 newtons, RB 0.14, and theoretical shear force is 0. In figure 8.7, weight 1 equals to 1.96, weight 2 equals to 3.92, and the force is 3.92. Experimental shear force is 0.02.7 newton, and RA is 0.159 newtons, and RB is 0.20. Theoretical shear force is 0.18. Figure 8.8, weight 1 is 4.91, weight 2 is 3.92, and force is 3.92. Experimental shear force 02.0 newton, RA is 1.181 newton, RB is 0.24, and theoretical shear force is 0.10. Support reactions RA and RB and shear force values vary based on the different load. Configurations weight 1 and weight 2 experimental readings did not perfectly match theoretical calculations, but the general trend of shear force increasing with load was confirmed.
Okay, my name is Muhammad Danish Taufi bin Hassan, and my matrix number is CD250132, and I'll explain about the discussion for the shear force experiment. Firstly, based on the graph, we can see an upward trend as the applied load increase. Both the experimental and theoretical shear force also increase. The theoretical graph forms an almost straight line, which shows that the shear force is directly proportional to the applied load. Next, this means that when a larger load is applied to the beam, the shear force inside the beam increases proportionally. And this result is actually consistent with basic beam theory. Next, when we compare the experimental and theoretical result, we notice that the experimental shear force values are consistently lower
than the theoretical values. However, both results follow the same increasing pattern. And technically, the difference between the two results may be caused by real experimental factors such as friction at the support and the pulleys, slight beam misalignment, small deformation of the beam, and possible reading or calibration errors. The theoretical calculation assumes the ideal conditions with no energy loss, which is difficult to achieve in real experiment. Overall, last but not least, the theoretical equation provides a good prediction of the trend, but slightly overestimate the shear force values. And based on that, despite this difference, our experiment successfully verifies that the shear force in the beam increase linearly with the applied load. That is all for the discussion. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMMAD and I'm going to explain about shear force of a beam in application in real life. So the first one, we have bridge deck and girders experience heavy loads from vehicles. As cars and trucks move across the bridge, the beam underneath carry vertical load that creates shear force. A proper shear design makes sure the bridge can safely handle traffic. And then we have building. So for building, floor, slab and roof beam in houses, school and office carry the weight of people, furniture and equipment. When this load push down on the beam, shear force develop near the support. So that engineers calculate this force to ensure the beam do not crack or fail. And last one, we have aircraft wing. Airplane wings act like beam as the aircraft move the upward lift on the wing, and the weight of fuel create bending and shear force. Proper shear strength help prevent structure failure during flight.
Okay, in conclusion, from the experiment on the shear force of a beam, it can be concluded that the shear force within a beam varies linearly between concentrated load change abruptly at the points of load applications. The experimental results were generally consistent with the theoretical values obtained from beam theory, showing that the concept of equilibrium and internal resistance in beam is valid achievements. The experiment successfully demonstrates the relationship between the applied load and the internal shear force distribution. The plot shear force diagram closely match the theoretical predictions, confirming understanding of shear behavior in statically determinate beams. The problems that we face, some errors occurs due to instrument calibrations, inaccurate load placement and slight reflection of the beam during measurement. Human error while recording readings also contribute to small deviations between experimental and theoretical values. For the recommendations for improvement, to improve accuracy, the experiment should be more precise measure instruments and ensure proper alignment of loads. Repeating the experiments multiply times and average the result can be reduced random errors. Additionally, digital data acquisition systems could be used to minimize human error.